Right, so can you see? So on the left, you should be able to see what's called a hydrothermal spring, on a submarine hydrothermal spring. And on the right, you can see a kind of provisional early rocket. And the point here is to try to compare the energetics of the two, because people don't seem to understand, for the most part, just what drove life into being. Of course, it's actually a disequilibria. And the disequilibria happens to be very similar on the early Earth to that we can think of as driving a rocket. So what I want to emphasize here, especially to this kind of audience, and that is that life on this planet was just all part of the development of the planet itself. So it was just it was the final processing of the planet after connection. On the right-hand side, I think say a typical rocket could have the electron-rich methane and hydrogen as a fuel, as a possibility, but of course you need an oxidant, and one oxidant is flaming nitric acid. And what happens here, of course, is you ignite the two and you can generate water and nitric oxide and carbon monoxide, and that gives you the thrust for the rocket. Now, one of the things about rocket science is that you absolutely do not want to have any intermediates. The intermediates are bad news, and they're, of course, polluting. The paradox in life is that you just need those intermediates, and you don't want to go to the entirely to carbon dioxide, for example. So what we have here as oxidants in the early ocean actually is nitric oxide or nitrate and nitrite. The actual fuels are the same, hydrogen and methane. They bubble out of these hot springs, and carbon dioxide is a very, very electron acceptor, but with help from the nitric oxide, then you can also reduce the carbon dioxide to carbon monoxide, and you can oxidize the methane and hydrogen to ammonia and a methyl group, and that will give you biosynthesis. And the biosynthesis are, of course, it's the intermediates. So I just want to get this point about energetics off the ground. So if we go on to the next slide, we can think about what the early world was like. Now, this is very well known now geologically, although most of the biologists and most origin of life people will not look at the geology and will not look at thermodynamics, which is very, to me, upsetting. So here's our early Earth, 4.4 billion years ago. It's just been formed, and the water has just condensed onto the planet. The rain now, probably about 1,000 to 10 years, give you an ocean that was uniformly 4 to 5 to 6 kilometers deep. There was absolutely no land on that early Earth. It was just a turbulent water world whirling at twice its present rate, at least. So the day is very short. You've got, of course, meteoritic impacts. You've got very high UV, between 10 and 100 times as much as today. And there's roiling waves up to 10 meters high. There's just nowhere to have a surface origin of life on this planet. So I just want to point out again, life is a continuum of planet formation. So if we go to the next slide, this is just to kind of bring to bear the point that some of you may have seen this, oh dear, what's it called? The Beverly Hill Cops program. And here's, sorry, somebody help me with the actor here. Anyway, doesn't matter. So what they're doing in the cop, this comes from Chicago, and he's so smart, much smarter than all the Los Angeles cops. So he knows how to stop the cop cars going, and by sticking bananas up the tailpipe, because it is the exhaust that drives your car. It's the exhaust that drives the universe. It's the generation of entropy that drives everything. You are pulled towards the generation of entropy. And in doing so, you get these various disequilibrium systems, such as convection and life, that help to generate this entropy. And of course, so we'll revert to Boltzmann's point, so beautifully put and hardly ever recognized, that the general struggle for existence of animate beings is not the struggle for energy, which exists in plenty in any bodies in the form of heat, but a struggle for entropy. That is low entropy, of course. You've got to have a low entropy site. So if you go to other people's view of how life starts, then you've got this high entropy suggestion that somehow or other organic molecules come from space, or they're brought in by the Murchison meteorite or some such meteorite, smashes into the earth and sheds off a few amino acids. And somehow or other, in this situation, everything amalgamates to become life. Now, we know that if we were to completely destroy any living system and you put it in that lake, nothing would happen. And yet people still keep thinking that somehow or other Frankenstein will come out of this lake. It will not. And I've just kind of remind us about how that the big waves are there. This is not Schrödinger's order from order, nor even Prigoghine's order through fluctuations. This is a suggestion of order from disorder. And we know to our sadness that history tells us that you cannot get order from disorder. So I'd just like to emphasize this pond model, to my mind, is absolutely hopeless mechanism. So let's go to what we do think, and this is what we do know, and that is here's the early ocean. It's rained out, there's rain everywhere, there's very hard UV. And the intriguing thing is you used to have what's called an upper mantle ocean. That is melted silicates, and they are still so mushy for the first 500 million years that they cannot support load. So although you can have convective systems and they might come to the surface in volcanoes and so forth, none of them will reach the surface of the ocean. So this is how we see the early ocean. So as I say, 4 or 5 kilometers deep. Here's an alkaline spring coming up into the early ocean. I won't go into details, but I can tell you that it's alkaline or basic, if you like. Its pH is about 10, perhaps 11. It's got hydrogen and methane and formate in it at about 100 to 120 degrees centigrade, so not too hot. It's interacting in the slide with carbon dioxide in the ocean. I've called it a carbonic ocean, and also the nitrate and nitric oxides that are generated by lightning in the early Earth, and with some carbon monoxide from the carbon dioxide and nitrogen. So we've got an electron acceptor, just like in that rocket. We've got carbon dioxide, which is the primeval molecule, the primordial molecule for life. And life still today is the generation, it all comes from life. That is the prebiotic molecule. Everything you had for breakfast and all the wooden chairs you sit on and tables, they all started life as carbon dioxide. So we think life itself started from carbon dioxide. And what happened was you've got the interaction between the, you've got, as the alkaline water comes up towards the ocean, then you get a precipitation of minerals, mostly iron minerals, with some nickel and molybdenum and so forth. They're called fuggerite, they are iron oxyhydroxides, and also a little bit of McKinowite, which is iron sulfide. So you've got the two together, and I'm going to go to the next slide to give a bit more detail. And this detail shows you the disequilibria between the alkaline spring that's coming up, which is pretty hot, but not too hot. So in other words, it's life can live up to 120 degrees centigrade or so. So it's not too hot. It comes into a cooler ocean, and we've got this disequilibria, which is mostly a redox, that is oxidation versus reduction. So hydrogen can react with carbon dioxide, with nitric oxide, methane can relate to nitric oxide, and so forth. And you've also got a big pH gradient of about 5 units, which is about 300 millivolts. So you've got so the electron voltage here is up to 1 volt. And that's what life lives off today. It's not too much, but it's also not too little. And most cells are using 1 million electrons a second. So basically, we have those electrons, and the electrons are supplied by hydrogen and methane, and the acceptors are, as I say, nitric oxide, nitrate, and carbon dioxide. And you make these kind of intermediate molecules like acetate and amino acids. So it's all about this disequilibria. And the proof of this, so to speak, is that the first iron formations, the first precipitates on the early ocean known to be the first precipitates are the iron formations, the banded iron formations, for which our whole iron industrial revolution took off from. So basically, you've got this iron that you've got the precipitate everywhere, but at the interface between the two areas, between the ocean and the alkaline spring, through this kind of inorganic membrane, this metal membrane, metal sulfide and oxyhydroxide membrane, that is where the interfacing takes place, and that's where the transitions take place. So if you look into the precipitates, and some of this may be strange to you, but all I'm showing you here is on the left-hand side, iron, nickel, nitrogen, oxygen, hydrogen, and so forth. And on the left-hand side, these are the mineral structures precipitated in that vent area. So you've got something called green rust on the left with iron and in the red color, and iron in the orangey color, oxygen in the red color. And you go down a bit and you've got nickel in gregite, something called gregite. You've got nickel and the iron there, and the sulfur is and violarites, another mineral, and so forth. But you go to the right-hand side, and you'll see that the early the early enzymes had exactly the same kind of central structure. So it seems to me that we've got life kind of handed to us on a plate. We don't have to go anywhere looking for the start of life. We've got a low entropy environment where everything, including the energetics, is supplied. So how we think of this is something called green rust. So this is one of the minerals it precipitates. And what you can see here is on the left-hand side, the ocean, oxide and nitric acid and so forth. On the right-hand side are the electron donors, that is the hydrogen and the methane and so forth, in alkaline solution. And the two interact through this mineral called green rust or fuggerite. We'll call it green rust because green rust is a very obvious kind of term. It is rather like red rust, except it's not so oxidized. And you'll see that there's interlayers between the iron oxides, which it can be ferric iron or ferrous iron, and you can see that you can pump nitric oxide in to, for example, or nitrate into one side, and within 2 hours or a few hours, you can add 8 electrons to generate methane. So it's not as fast as life makes it, but you can imagine, to make ammonia. And you can imagine, of course, amino acids and nucleic acids need ammonia. So this produces ammonia on site for the amino acids. So we know that's for sure, that's all published. What we don't know, we also know that we can make NH2 there, and we think that, and we haven't managed to do this in the lab yet, but we think we could make hydrazine from there, which of course is a good rocket fuel, but also a good start for making nucleic acids and other organic enzymes. So in other words, you can put things together. You can, we know also in the lab, we've managed to mix ammonia in one of these interlayers with something called pyruvate and made alanine, which is an amino acid. And if you were to join those amino acids together, they can act as kind of little nest sites for these metal ion centers, which are the catalytic sites in enzymes, and even to the extent of making something called amyloid, which like prions, which of course we know as a disease, but also their typical structure for proteins or crystalline proteins, and they can act as the new membrane after the iron sulfides and the iron oxyhydroxides have been used up. So it's rather like a ramjet. We actually ram the nitrate and the carbon dioxide into one end. You kind of ignite it through the catalytic effect of oxidizing to iron 3+, and the exhaust is just what we want. It's not a very good exhaust for a rocket or a ramjet, but it's a very good exhaust for life because there's so many intermediates associated with it. So we put the whole thing together, and on the right-hand side, we'll see one of these vents that have actually been discovered. One of the good things about this alkaline vent hypothesis is that it was predicted, these vents, in 1989, and the vents were actually discovered in 1999 to 2000. They're called Lost City. They occur in the Atlantic, and they're made of a mineral called brucite, and you can see it's very similar to green rust, which we would say was the mineral that was precipitated in the anoxic conditions of the early Earth. So these are the first enzymes, they are the first make the first membranes, and they allow energy transfer to generate organic molecules on the early Earth. And from then on, of course, you can get to RNA, DNA, and so forth. I think I'll stop there just in case there's questions, and I'm sure I've taken my time up. So thank you very much.